Okay, so uh, we're looking at these multivariable functions. We looked at differentiation. Now we're going to look at integration. We'll start off with double integrals. Before I do that, I want to go back and just remind you how we developed the whole idea of the definite integral with single variable. And what you have to remember about integrals, when we talk about integrals, what we're talking about is adding a bunch of stuff up. In fact, we're adding an infinite amount of stuff up. And the first thing that we added up were rectangles, right? We added up areas of rectangles. And in the two dimension, of course, we've got the x and the y, and we've got, so in this case here, I've drawn a curve, and what I've done is I've partitioned off this curve. Now, I've not, and what we're trying to do, the way we introduced integrals was we said we're going to think of it as area. Because what we can do is we can add up the area of rectangles, and we found that that's a fairly good approximation for the area bounded by the curve in the x-axis, provided the curve is above the axis. So it was a convenient way to think about integrals, or this idea of summation. Now, here's what I've done. I've taken this curve from A to B, and I've partitioned it off, and I've got intervals here that are not the same. And what I've done is I've made rectangles. And I have the area of this rectangle. This is area 1, area 2, and so forth. And it looks like I've got 1, 2, 3, 4, 5, 6 rectangles here. Now, and it's important to note that you don't have to have equal widths. So I made these deliberately with unequal widths. Now remember what we did was we said, okay, I'm going to take this first rectangle, so I'm going to add up all these areas and try to figure out what the approximation for the area is under this curve. So the first thing I did was I said, okay, this first rectangle is going to be f of x1 times delta x1. That's that first rectangle. The second rectangle, of course, is f of x2 delta x2. And you can see where I'm going with this. I've made it so that I could just f of x3 delta x3, f of x4 delta x4. So I'm right here, and I made it so that the height that, this rectangle comes up here to f of x4. And we keep going. Now we've got f of x5, delta x5, and finally, the grand finale, f of x6, delta x6. Okay? So if I add up those rectangles, if I add up the area of those rectangles, what I'm going to get is an approximation for the area under that curve. And so what we did was we said, well, okay, so that's an approximation, and it might not be a very good approximation if our intervals, if there's too much of this business going on, if there's too much of this like this right here, right? We've got part of the curve that's not contained in this rectangle. So if we have too much of that going on, our approximation is not going to be very good. And what we said was, well, let me write this as a summation. We've got this. I could write this as f of x sub I, delta xi, and I have I going from 1 to 6. Okay? And we said, okay, that's going to be our approximation. Now, we learned this, that the more rectangles we have, the better approximation. So maybe I want to make more intervals. And in fact, I want to do this. I want to say, well, I'm going to take the sum, f of xi, delta xi, and I'm going to let I go from 1 to n. So there's going to be n rectangles. And we found this, that the more rectangles we choose, the smaller the largest interval between them. Right here, look at this largest interval here, delta x2, right here. The more rectangles we have, the more the largest one goes to 0, and the better our approximation. So what we did was we said this, well, let's just take the limit as the largest one of those rectangles goes to 0. In other words, the largest partition. Now this right here, this stands for the norm of the partition. And it denotes the largest delta x. So what we're saying is, if you take the largest delta x and let it go to 0, then all of them go to 0, right? And we define that to be the definite integral. Okay, so that's how we define the definite integral. Okay, everybody remember that? Now, when we go into 3 dimensions, we have to think a little bit differently. We have to expand the way we look at things, because in the 2 dimensions, we talk about the area under a curve. But in 3 dimensions, we don't have a curve, we have a surface. And we don't have area, we have a volume. So let's look at some pictures that since I'm not very good at drawing, what I did was this piece of paper here, you'll notice there's a region there. Okay, I've just drawn a region there, and this is sort of like on the XY axis. I start at x equals a to x equals b, and I've got an interval. Well, now I've got a region. Now imagine that there's a surface. This thing right here is a surface, and below that surface is a region. Not an interval, but a region. And here's a topical view, right? You can see through the surface down at this region. Now what I want to do is, I want to think of the double integral. I want to introduce the double integral as getting the volume of this solid that is bounded between the surface and that region down there. So you know it's not just going x to x, or x goes to a to b. There's also the y component. And I'm going to proceed in a similar fashion the way I did in single variable calculus, except instead of using rectangles, I'll use rectangular prisms, right? Because it's 3 dimensions. So I've got these Legos. So you can see I took this region right here, and I made some rectangles there. Okay, rectangular prisms. Do y'all see that? It looks like I've got 8 of them. Any questions about that? Okay. Now, what I want to do is I want to go from this picture and just look flatly. I want to just look at the XY axis at this region. So let's go down here and just look at this region. Here, these are the bases of my prism. Okay, that's what this is. Okay, so does everyone see what I have here? What I've done is I'm just looking at the flat XY axis, and this is my region, and these are the bases of the prisms, the 8 prisms. Now let's suppose this. Let's suppose that the surface actually passes through f of x1, y1, f of x2, y1, and so forth. So that I've taken these points right here in the center of these prisms, and let's suppose that the surface actually passes through those points such that there are values, right? So f of x1, y1 is equal to 1. F of x2, y2 is equal to 2, and so forth. Now, what I want to do is I want to calculate the volume of each one of these prisms, and I'm going to use it as an approximation for the volume underneath that surface. So here's what I'm going to do. I'm going to take the first one. So I'm going to take this first prism right here, this one, and I'm going to say, okay, this is, and for simplicity's sake, I've made the delta x and the delta y's the same. Or I've made them to not change in value. Okay. So the delta x is the same for each prism. The delta y is the same for each prism, just for simplicity's sake. Now, notice what I have. The volume of this first prism is going to be the height times the area of the base. Do y'all see that? So the area of the base is delta x, delta y. Okay? Does everybody see that? Now, let me go the second one. The second one is going to be f of x2, y1, delta x, delta y. Y'all see that? So I've got that one. The area of the volume of the prism of the next one. And you can kind of see how this game is played, right? And then finally, the next one, x4, y1, delta x, delta y. Now, what I've done is, notice the y hasn't changed. I've fixed y, right? It was y1 for each one of these, y1, 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 y1. The x is incremented, right? Now, let me go to the next, let me go up here. Now I'm going to get these ones. I'm going to get these volumes. So now I increment y up to the next level, and I've got this. I've got f of x1, y2, delta x, delta y. See that? Plus f of x1, y2, delta x, delta y, plus f of x3, y2, delta x, delta y, and the grand finale, let's see here, this should be x2, y2, okay? And then finally, f of x4, y2, delta x, delta y. Now, you can see what we've done there is we've got 8 prisms, we've got the volume of each. If we add those up, that will approximate the volume below that surface and above our region. Now, let me introduce some notation to you. What we can do, I'm going to introduce this double summation notation. And what I'm going to say is, I'm going to say, okay, let's look at the y's. How do the y's go? The y's, which I'll say is j, they go from 1 to 2, right? And then we've got the x's, and the x's I'll just call k. They go from 1 to 4. Now, here's the way this double summation works. You use this outside sum, and you're going to fix the y. So notice I fixed the y. I've got y's fixed at 1, and then I increment the x's. And then after I go through y1, then I increment y's, and then I've got y2, and I increment the x's again. Y'all see that? That's the way this summation notation works. So what we've got then is we've got x, x sub k, y sub j, and then we had delta x and delta y to be the same. It doesn't have to be, but we'll just do it that way. Okay. So this is another way, this right here, this double summation notation is just another way of writing out all of this stuff. Okay. Any questions? Now, we proceed with the same reasoning we did with single variable calculus in that we say, well, if those 8 rectangular prisms will give us an approximation for the volume, maybe more rectangular prisms will give us a better representation. So here's the way we think about it. We go through here and we say, okay, let's just be general here. Okay, so I'm going to sum up. I've got j equals 1. Well, let me just do this. Instead of writing it this way, let me just say I'm summing across the j and the k right there. I just won't put an upper bound. We just know we're summing. And then I've got f of x sub k, y sub j, delta xk, delta yj. And I'm going to do this. I'm going to say, now, I'm going to do just like I did in single variable calculus. I'm going to take the norm of the partition and let it go to 0. Now, you might be saying, well, what in this case is this partition? Well, what we're saying is, think about this. Think about each one of these rectangular prism bases, and think about a diameter going across. Okay? So each one of these has a diameter going across. I'm going to say, what if I let the longest diameter go to 0? And that's what this thing is, right? I'm letting this thing, the longest diameter, go to 0. When that happens, what we get, just like single variable, we get a double integral over that region, right? So we're going to get a double integral over that region, and it's going to go like this. It's going to go f of xy dx dy. Okay? So that's going to be our double integral. Okay? Any questions about that? That r is the region. That r is, we're just saying we're integrating over this region. We could have made up some, x1, I could have put x1 there, x2 up there, and so forth, but I'll just put it over the region. Okay? Any questions about that? Now, so let's see how this might work. And we'll start off with something that's intuitive. Let's suppose that we've got some function. Let's suppose that f of xy equals 6. In other words, this is like just a horizontal plane above the xy axis, right? Above the xy plane, right? This is like z equals 6. Now, what I want to do is I want to find the volume below this surface and above the xy plane on this interval. I want to make it so that x goes from 0 to 2, and I want to make it so that y is from 0 to 3, let's say. Now, this just will give us one big prism, right? Rectangular prism. And we know the volume, right? It's the area of the base times the height. So what I'm trying to do is show, well, how do these double integrals, how are they evaluated? Well, here's what's going to happen. We're going to have x go from 0 to 2. And it doesn't matter if you put x first or y first. I'll just put x first. And then y goes from 0 to 3. And I'll put in here the 6. Now, since I'm going to integrate with respect to x first, I'll do the dx there and then the dy here. So notice this dx tells you, okay, integrate with respect to x and view y as a constant. So, and then evaluate it from 0 to 2. So here's what's going to happen. I'm going to have 0 to 3. Now notice, if I integrate this, I'm going to get 6x going from 0 to 2 dy. Everybody see that? Which is going to be the integral from 0 to 3 of 6 times 2. I didn't multiply it out yet. Okay. I'll just leave it like that for now. Now, then I go back and integrate this one. So here I go. I'm going to integrate from 0 to 3. So I've got 6 times 2y from 0 to 3. And that's 6 times 2 times 3. Now, that is the volume of that prism, right? It's the length of the base times the width of the base times the height, right? Length times width times height. So this is one of the things that we knew how to do this one. Okay, any questions about that? Okay, now what I want to do is I want to look at one that's a little more complex. I'll just put an integral up here and we'll see about evaluating it. Let's suppose I want to go from 0 to 1, and I've got this. I've got x squared plus 2y squared, and I want to do this. I want to integrate first with respect to x, and then with respect to y, and y is going to go from 2 to 3, let's say. Okay. Well, so here we go. I'm going to integrate with respect to x first, so y is just viewed as a constant. So 0 to 3 is what I have for this integral over here. 2 to 3. Sorry about that. 2 to 3. Okay. Now, the integral, it's going to be 1/3 x cubed plus 2y squared x. And you're going from 0 to 1. You see what I did? Y squared is a constant. So, if I was differentiating with respect to x, that y squared would be gone. But I'm not. So now I evaluate this. So let's see what I get now. I got 2 to 3. This is going to be 1/3 times 1 cubed plus 2y squared times 1. and then minus the 0, but that's just going to zero out, right? And then here's dy. So let's clean this up a little bit. I've got 2 to 3, and this is 1/3 plus 2y squared dy. Now we're right back to single variable calculus, right? Okay. So let's see what happens here. This is going to be 1/3 y plus y cubed, and we're going from 2 to 3. Yeah, 2/3. Okay. Any other observations or questions about that one? Now we know how to proceed from there, right? Just plug in the 3 and then minus plugging in the 2. So we won't go, we won't do that. Does everyone see how to evaluate these then? These double integrals. Okay, you work from the outside. You know, the dx indicates you integrate with respect to the x, and then the dy with respect to the y. And you can change order for these. You don't have to go in that order. You get the same thing. Now, I want to look at a couple of things here. Let's suppose that we've got, let's just look at the difference in these two integrals. Let's suppose I've got xy, and I'll say, let me just say dx, dy. I could just say dA, Sometimes you'll see this written as just d capital A for the area of the base. But let's suppose I've got this integral. Now this is going to give me volume, right? What do you think would happen is if I did this? What if I didn't have f of xy in there as anything but 1? Let's suppose f of xy was just 1. In other words, we had this integral. What do you think that would be? Yeah, it would just be area, right? It's like we're taking the delta x times delta y times 1. It amounts to the area. So here's volume and here's area. So let's just look at an example. Let's suppose, and this is, this would be reminiscent from Cal 1. But let's suppose that we have our x-axis, our y-axis, and we have a couple of functions. We have the square root of x, and we have x squared. Okay. Let's suppose that we have these two functions, and what we want to do is we want to find the bounded area. Now we know how to do that with just single variable. What we would do is we would integrate from 0 to 1, because that's the intersection, right? It intersects here at 0, intersects here at 1. We take the top function minus the bottom function. We know this would give us the area here, without question. Now, let's do this. Let's solve that same problem with double integrals. Well, here's what we would do. I'm going to integrate first with respect to y. And I'm going to go from the bottom function, x squared, to the top function, the square root of x. And then I'm going to integrate with respect to y. With respect to x. And x goes from 0 to 1. Okay? So notice, I integrate it first of all with respect to y. And then I integrate with respect to x. Okay? So dig what happens now. If I do this, I'm going to have the integral from 0 to 1, and then this one is just going to be y evaluated from x squared to the square root of x dx. Well, if I plug that in, I'm going to get the integral from 0 to 1 of the square root of x minus x squared dx. And you see that you get the very same integral, right? So you can use double integrals, to find area. It's not just finding volume. You can find area. Okay. Any questions about that? It just depends on how you want to look at it. Single variables, using that method's fine. Any questions about this?